Welcome back to another Forge College Explainer. All right, let's just jump right in. Have you ever tried to definitively compare the Ethereum virtual machine to the Solana virtual machine? If you have, you know you usually just end up drowning in this chaotic sea of apples to oranges data. It's a mess. But today, we are going to fix that. We're laying down the blueprint for a rigorous, completely repeatable comparative analyzer for both EVM and SVM architectures. Here is our exact blueprint for today. First, we'll look at the trop of bad comparisons. Then, drawing the boundaries. Third, the metrics that actually matter. Fourth, building the evaluation rubric. Fifth, normalizing with a harness. And finally, your next steps. Let's do this. Section 1. The trap of bad comparisons. You know, it's actually kind of funny. Web3 developers build literally some of the most incredibly complex cryptographic systems on the planet, right? But when it comes to comparing blockchains, they usually just rely on chaotic arguments on social media. It's the Twitter way. You've seen it. It's full of emotional arguments, completely conflating entirely different layers. People are always shouting about high throughput without ever actually defining the underlying hardware. We need to move to the engineering way. Consistent scope, normalized baselines. Without consistent evaluation criteria, all those little microbenchmarks you've collected, they're basically useless. We are swapping out those Twitter anecdotes for a rigid academic framework. Section 2. Drawing the boundaries to calibrate our instruments. Okay, so before we look at a single metric, we absolutely have to calibrate our instruments. We cannot accidentally conflate causes and effects here. Think about it. If a chain feels really fast, is it because it has a highly optimized virtual machine? Or is it just running on massive supercomputer nodes? To figure that out, we have to separate our comparison into 3 strict non-overlapping domains. Step 1 is the execution domain. This is strictly how instructions run and are scheduled. Step 2 is the state model. This is how the account and storage models allocate and actually persist data on the ledger. And step 3 is the runtime environment, which covers the node architecture, the parallelism model, and deployment constraints. Separating these 3 things is absolutely crucial so you don't mistakenly attribute virtual machine performance differences to, say, node hardware choices. Section 3. The metrics that matter. So in the previous module, we collected all our raw materials, right? Those incredibly detailed JSON trace artifacts that represent actual transaction workloads. Now, we need to figure out exactly what to extract from them. And notice how we handle the platform differences here. To measure execution accurately, we have to pull very specific JSON fields. For the EVM side of things, we're grabbing gas used and VM op count. But over on Solana's C level, we're looking for compute units alongside state write bytes. Our code basically has to map these wildly different platform-specific names into a single unified parsing path. Section 4. Building the evaluation rubric. This right here is the absolute core of our methodology. Sure, we have raw data, but raw data needs a rubric before it can become an actual scored assessment. When you look at the metrics, that direction column is key. For something like throughput, we obviously want a higher number. But for latency, lower is actually better. We also weigh things like determinism and developer ergonomics based on what the stakeholders actually care about. Like, if the audience for your capstone project is laser-focused on state minimization, well, we might bump up that 20% weight on state delta per TX and lower something else. This rubric is what mathematically turns raw, unfeeling numbers into a score that stakeholders can actually use. Section 5. Normalizing with the harness. But here's the million-dollar question. How do we fairly score an EVM gas unit against a Solana compute unit? Well, we use a Python parsing harness as our main engine. It's a completely reproducible workflow. Step 1, extract. We parse those JSON fields we were just talking about. Step 2, normalize. We divide those raw numbers by baseline means to create a totally level playing field. And step 3, score. We apply our rubric weights. This workflow is a real game changer because it lets us build derived metrics to compare things that previously seemed completely incomparable. Let's take compute intensity, for example. It's literally just the number of virtual machine operations divided by the build unit. Now, for EVM, that build unit is gas. For SVM, it's compute units. By setting it up this way, it strips away all those platform-specific accounting illusions and shows us the raw computational density. We're measuring the actual operational work performed per unit of build compute across entirely different platforms. Next up, we have the normalized cost index. This mathematically combines gas and compute units, normalizing both of them by their respective baseline means. And I cannot stress this enough. This specific formula is the secret sauce to fairly comparing completely different billing models. By dividing the raw usage by a representative baseline, we literally convert apples and oranges into a single standardized cost percentage. But what happens when you change that baseline? Or what if you tweak the rubric weights? Well, this introduces a really vital engineering concept called sensitivity analysis. By playing around with the weights in our code, say bumping them up or down by 10%, we can see exactly how much the final score changes. Think about it. If a platform only wins because we gave one metric a massively skewed weight, our conclusion isn't actually very strong, is it? Sensitivity analysis proves which of our architectural conclusions are genuinely robust, no matter how you try to tilt the scales. Section 6. Next steps. So, we've got the data, we've got the scoring harness, now we need the narrative. Your final technical capstone document absolutely must be structured to ensure your measurements map perfectly to a persuasive story. You want to start with an executive summary featuring your scored highlights. Next, clearly lay out your baselines in the scope and methodology section. Then, you're going to mirror our system boundaries, execution analysis, state analysis, and runtime considerations. And finally, your recommendations. You aren't just dumping a bunch of data on a page here. You are guiding the reader through a mathematically sound, completely impartial comparison. So, I leave you with this final question. Are your instruments ready for the ultimate architectural showdown? Because in our next lesson, Methodology and Metrics for Evaluating Architecture, we are going to take this exact rubric and unleash it on concrete measurement protocols and actual real-world network deployments. Thank you so much for hanging out with me for this Forge College Explainer. If you want to learn more about this subject, access the full source code for our scoring harness, or just dive deeper into other Web3 topics, be sure to visit forge.college. I will see you in the next one.